It has been long, really, because I have met you in 2012.
That would have been when you were doing your high secondary, no?
Yes.
Okay. Just hold on. I have to just open the door. Somebody's come. Okay,
Yeah.
I'll just be back. So I can't see any of the participants in this mode, is it?
Yes, that's the issue actually. Won't be able to see the participants.
Okay.
So this is actually one of the first time like we are doing this kind of very interesting talk, because IEEE is mostly related to engineering and electronics. So like we thought like it will be something a different kind of experience for all of us.
Okay.
And,
Okay. So most of the participants will be engineering students, or?
Yes, it will be mostly from engineering background, although there will be mixed participants as well.
Okay.
Hi Dhruva, this is Jaikumba. I'm also here.
Jaikumba, how are you?
Doing good. I'm here to attend your talk after several years. I'm going to hear you.
Wow. You're in Roorkee, right?
Yes.
Fantastic. So the ASI went off very well from whatever.
Yeah. It went really well.
Congratulations to all of you.
Yes.
Hi Jaikumba. It is Devolina here.
Okay, hi.
Yeah, I was your classmate from Cotton, first year.
Oh, okay.
Yeah, you were from Vivek. Huh?
Yeah, Vivek's batch, yeah.
Yes, Vivek batch, Payal.
Yeah, Payal, Vivek's same batch.
Nice to have you here.
After all, it's a small world, you see.
It's a small world, yeah.
So Devolina, this is Vivek Day, is it? Or is it some other Vivek?
No, Vivek Thapa.
Vivek Thapa,
yeah. He's in nicer now, isn't it, Bhubaneswar?
No, he's in Jodhpur.
Jodhpur. Yeah, Jodhpur. Yeah. Okay. Yeah. So he's working on theoretical models of neutron stars, no?
Correct, yes.
So we'll start at around 6:05 because participants are joining right now.
Sure. I'll just get myself a cup of water.
Yeah,
I'll be back in a few minutes. Yeah.
Yep.
So Debolina, you are from which branch? Which?
I'm doing my MS from IIT Kharagpur, EC.
No, in Cotton, you are from which branch?
I was in mathematics.
Oh, okay, maths.
Yeah.
So you may be Ringsangdi's batchmate, right? So
yes, Ringsangdi. Yeah, Ranjit.
Sir, with your kind permission, can we start the
Yeah, absolutely. You're welcome.
yeah, because we have already 25 number of participants and more will be joining, and someone will be also there from YouTube that will be doing the streaming part. And so can I share my screen? I will just have a couple bit of introduction.
Okay, you want me to stop sharing?
Yes, just for a few seconds.
Okay, 1 second. Where does the stop sharing come in?
Yeah, you have to go to the Google Chrome again.
Google Chrome again, no? Yeah. Okay.
Yes, stop presenting.
Okay, fine.
Yeah. Good evening, everyone. So first of all, I would like to thank Professor Dhruva Saikia sir to give his valuable time for us, and like so that we can really have some interesting talk. Being an electronic organization, it will be really like we are very closely related because we work on microwave, and as per I remember, like for cosmic microwave background, we also have a Nobel Prize going on, and the people are exploring in this really exciting field, like rather than like and kind of some interdisciplinary work. So before going to the talk, I will be just introducing a bit about our chapter and the activities that we are going around. So we are basically an IEEE AP-MTTS student branch chapter based in IIT Kharagpur in IEEE Kharagpur section. So in our chapter, we basically focus on the topic of antenna propagation and microwave theory and technique society. So like we have various talks going around. So like if you can scroll our website, so all the updates about the talks that have recently been held are being given here. Along with that, we also like to mention that in 2021 we got this very like prestigious IEEE MTTS Outstanding Chapter Award for our activities. Beside that, we have been also quite active, not only on organizing technical talks from all over the world. Now we are going to this virtual mode, but previously we also have this physical meet. Not only holding talks, but we also organize workshops for college students, as you can see from the previous work. And we also have been involved quite a bit amount of activities related to social activities, where we teach school children. And one of such activity that was quite popular was like during back in 2020 in December in Assam, where a team of dedicated volunteers have been involved in teaching schools at regional levels. So this was one activity, and with the help of this, currently we are on an ongoing project funded by SITE, where we are opening labs at such remote locations. So as part of now, 2 locations has been fixed, 2 from Assam and 1 from Kharagpur itself, and we have been quite a bit active in this talk. So now without much further ado, like I also want to introduce there have been persons like that have been involved in this. So at this current term, like we have our Vice Chair Ananya De, our Secretary Mr. Satya Prakash, Assistant Secretary Govind Vehra, our Treasurer Ms. Debolina Deblath, Assistant Treasurer Mr. Suraj Kumar Singh, Webmaster Miss Anuradha Gupta, Assistant Webmaster Ms. Tina Ajay, Shreya Ghosh as our Publicity Coordinator, Rajeshri Sen as our Creative Writer, and Anup Sharma from Dibrugarh University as our Regional Coordinator. Do please feel free to contact us. Along with this, we also have our SEC members, like the students from IIT Kharagpur and also from regional coordinators from Dibrugarh University, that has been involved widely in all the voluntary activities that is going around. And I would also like to thank all our volunteers for this, and you can definitely scroll our website to get more information regarding our activities that we are currently going on. I'm also sharing our link. You can also visit our LinkedIn as well as Facebook page along with us. So without any further ado, I would ask our Professor Rajat Roy sir to kindly introduce Professor Dhruvo. Professor Rajat, can you hear us?
Yes.
Yes, Professor Rajat, it's to you.
So welcome, Professor DJ Saikia, to this talk. I hope you will benefit from, although we are not in this branch, but still there will be some link between microwaves because as Paula said, that the microwave background, cosmic microwave background, is one of the tests of the Big Bang theory. So I just, instead of wasting time, I will just give the biodata of Professor Dhruvo Saikia. Professor Saikia was a professor at the National Center for Radio Astrophysics of the Tata Institute of Fundamental Research, where he worked for over 40 years and now heads the Teaching Learning Center and the National Resource Center of the Inter-University Center for Astronomy and Astrophysics, IIT. His research interests are on different aspects of extragalactic astronomy and astrophysics, especially active galaxies, and more recently on education, with an emphasis on higher education. Besides TIFR and IUCA, he has been engaged in research and teaching at the Jodrell Bank Observatory of the University of Manchester, National Radio Astronomy Observatory USA, Queen's University at Kingston, Canada, Australia Telescope National Facility CASS of CSIRO Australia, the University of Western Australia, and Savitribai Phule University and Cotton University, India. He has published over 150 research papers on leading journals and on and co-edited 2 volumes, Low Frequency Radio Universe, Astronomical Society of the Pacific 2009, and D.A. Green, Y. Gupta, and P. Venturi Fluid Flows to Black Holes. With D.A. Green and Y. Gupta and P. Venturi Fluid Flows to Black Holes. A tribute to Chandrasekhar on his birth annual centenary, World Scientific 2013, with Virginia Trimble. He was the founding Vice Chancellor of Cotton University at Guwahati. He was awarded the Professor N.K. Vainu Bappu Gold Medal of the Astronomical Society of India and is a Fellow of the National Academy of Sciences, India. So welcome Professor Saikia for this talk.
Thank you very much, Professor Rajat Roy. And I'll try sharing my screen again, and let's see, hopefully it'll all work well. Okay, present now. I should do entire screen. I should choose, I should share. Okay. You can see the screen, but not in screen mode, right?
Yes.
Let me put it in screen mode now.
Yes.
From beginning. Is that all right?
Yes.
I'll make sure it moves. It's moving?
Yes.
Okay, and you can hear me clearly?
Yes, Professor.
Okay, fantastic. Okay, thank you very much, Professor Roy, for the introduction. And let me first thank Pallab, Ananya, Satya Prakash, and the entire team for this very kind invitation to speak to you this evening on the theme of black holes in our universe. And what I've shown over here is the image of the black hole in a nearby galaxy called Messier 87. And this is perhaps the only image of a black hole which has been made so far. And making this image has actually involved all the ideas and concepts of antennas, signal processing, and this has been done at millimeter wavelengths. So I thought I would show you this picture just to illustrate to you the importance of actually the technical aspects of digital signal processing, understanding of antennas, understanding of how these antennas work, and how you can combine signals from different telescopes or different antennas to synthesize an image, which is just about 42 micro arc seconds across in diameter. This image was published about 3 years ago this month, exactly 3 years ago this month, and data was taken in 2017, and this result was announced in 2019. So what you can see in this image is a silhouette of a black hole in the center, from which, as you all know, light cannot escape. And what you see around it is where the photons and the plasma are emitting. And the slight asymmetry which you see over there in brightness is because of relativistic motion, where the plasma is moving around because of the presence of a supermassive black hole of about 6.5 billion times the mass of our sun that is moving around very rapidly. And when it is moving very close to the velocity of light, relativistic effects become important, and that is why you see the slight brightening when plasma is coming towards you. Understanding this thing involves a lot of physics in terms of both the way light rays bend in strong gravity. We'll not get into all the details, but I will try to give you a flavor of black holes. This is the Galaxy M87. M stands for Messier. Messier was an astronomer who was interested in comets, and he made a whole catalog of objects so as to not confuse himself with other celestial objects. So Messier's objects are some of the most beautiful objects in the sky, which you can sometimes see with the naked eye, but at least you can see with a reasonable sized small telescope or an amateur telescope. This particular galaxy, this particular black hole occurs in the center of this galaxy, as I said, which is just 16.8 megaparsecs away. I'll keep using this term, but just to remind you what it means, that 1 parsec is about 3 light years. Okay, that's about 3 into 10 to the power of 18 centimeters, and this is about 16.8 million parsecs away. If you want to convert it to light years, just approximately multiply by 3, and that's what you will get. So right from the center of this galaxy, way back in 1918, Herbert Curtis noticed there was a stream of light which was coming out. This is a more recent image. This is not Curtis's original image. And he noticed in the publications of the Lick Observatory that a curious straight ray lies in a gap in a nebulosity, apparently connected with a nucleus by a thin line of matter. The ray is brightest at its inner end, which is 11 arcsecond from nucleus. Those were the days where, black holes were not really taken seriously, although there was speculation earlier, as we shall see in a short while. And even plasma, one did not know what it was all about. It was left to Bard and Minkowski, who actually observed this filamentary kind of structure. They took a spectrum of it, and they found that this feature was actually coming towards you at a velocity of about close to minus 300 kilometers per second. And they were the first ones to use the word jet. Several condensations are on the outer parts of the jet, which extends about 20 arcseconds from the nucleus. And they looked at the emission lines of oxygen. This shows that it is the forbidden transition of singly ionized oxygen. But at that point of time, already used the word jet, which means that there is flow and there is plasma over there. But one didn't really know very much about what it consists of, the physical state, with what velocity, already measured the lines. Could it be the line velocity itself? Is there some underlying motion? One does not really know. Today, for this galaxy, we have a whole range of images. I've shown you on the left an image of this galaxy called a radio galaxy. The optical galaxy sits right in the center over here. It's an elliptical galaxy which you just saw. And right from the center, there is a jet of plasma which is squirting out. And today we know by monitoring the motions of these knots that these knots, some of these features, are moving at nearly the velocity of light. These three images all made at different radio frequencies. And this one is from the Hubble Space Telescope. These two are radio images made with very different angular resolutions. As students of engineering, you will know about Fourier transforms. So what very high resolution does is that when the antennas are far apart, it samples the Fourier components leading to small scale structure, whereas when the antennas are closer together, they sample the large scale structure. So you need information on all kinds of scales. And this actually goes much, much smaller. This is buried right inside over here, just 1/100 of a light year. And this you can see is 4,000 light years is the scale over here. So you need information on all kinds of scales. So this is the black hole which is giving rise to these jets. And this is the same jet which Herbert Curtis noticed in 1918, like a filamentary kind of structure which he noticed. This was the first jet from what are called active galactic nuclei which was discovered. Now, why do I use the word active galactic nuclei? Because galaxies are known to be an aggregate of millions or billions of stars. But for a small fraction of these galaxies, maybe about 10 to 20%, they're very active in terms of having all kinds of exotic activity like the spewing of jets at relativistic speeds, which can go over distances of millions and millions of light years. Generation of this energy and how it's get transported over such large distances continues to be an interesting area of research and poses all kinds of interesting challenges. I showed you an image of the Event Horizon Telescope. I'll tell you a little bit more about this telescope. And this has been used to zoom into not our galaxy as well, the black hole sitting in the center of our own galaxy, which we will get to listen to a little bit more about later. Here is another interesting galaxy called Centaurusy. It's a relatively nearby galaxy. It's only about 3.8 million parsecs away. You can multiply by roughly 3 to get it in light years. The extent of this radio emission you can see is about 500 kiloparsecs. But if you compare it to the size of the moon, it's about 16 times the size of the moon. And right in the heart of it is what the Event Horizon Telescope is trying to look at the black hole, trying to look at the jets, how they are forming. And the angular resolution which the Event Horizon Telescope has managed to look at the black hole is like the resolution you would require to look at an orange on the moon. That's the kind of resolution that one is being able to get at a frequency. This is about 230 gigahertz, which is at a wavelength of 1.3 millimeters or so. What is the Event Horizon Telescope? That was really a collaboration, an international collaboration, which has been put together by connecting telescopes from the South Pole to Greenland. And this is still growing, Hawaii to Europe. And these are some of the telescopes which have been sort of put over here. They all operate in a microwave region. They're all millimeter wave telescopes. And you want to go to millimeter wave region because you want to get high angular resolution. You want to get high angular resolution because you want to probe right into the nuclear region of active galaxies, or you want to see the fine scale structure either a black hole or just around it, because per se, the black hole itself, you will not be able to see, but the effects of it in the vicinity of the black hole. So how does this work actually? To get the angular resolution, as students of physics in your earlier days you would have remembered from Rayleigh's criteria, is approximately the wavelength divided by the diameter. So now in a single antenna, for example, if you look at the main beam, the half power beam width of the main lobe of your antennas is roughly given by lambda by t. So it's the same physical principles that are involved. But from a single antenna, and because the wavelengths are large, you will not be able to get the kind of resolutions we are required to look at probe black holes or the nuclear regions of galaxies. You need higher resolution. And a high resolution you can get by combining the signals from different antennas as though they're all in phase and they're all from a single antenna of the size determined by the separation between the furthest antennas. For example, with the Event Horizon Telescope, you're effectively using the diameter of the Earth as the longest baseline from the South Pole to Greenland. But this is an interesting project which has been going on, yielding exciting results very, very frequently on different kinds of active galaxies. To give you an idea, again, I said an orange or an apple on the moon. Just to give you an idea that if you had a 5 rupees coin, and you put it at a distance of 100 meters is something you're familiar with, it'll give you an angular resolution of about 47 arcseconds. 47 arcseconds is roughly the resolution of the human eye. It's similar ballpark, about an arc minute or so. If you put it at 1,000 kilometers, maybe Kharagpur to Dibrugarh, then it'll be about 4.7 milliarcseconds. Today, we are doing not in milliarcseconds, we are going to microarcseconds by trying to probe the deep interior regions where the black holes reside. This picture over here shows you an image of the very long baseline array. And that has from the Virgin Islands to Mauna Kea and Hawaii, exclusively devoted to very long baseline interferometry, as it is called, where you combine the signals from distant antennas. It's difficult to get them via cables, but you record them and process them later and try to synthesize an antenna, which is thousands and thousands of kilometers across. That is how we probe the inner regions of these nuclei. As I said, the two galaxies which I showed you, Messier 87 and Centaurus A. Centaurus A is the most luminous radio source towards the constellation Centaurus. They belong to a class of active galactic nuclei where there is very unusual nuclear activity going on in a galaxy rather than just the evolution of the stellar populations. Here from a region which you often cannot resolve except with telescopes like the Event Horizon Telescope, there is a luminosity of the order of 10 to the power of 43 to 47 Earths per second. To give you an idea, the solar luminosity is about 10 to the power of 33 Earths per second. So this is about 10 to the power of 10 to 10 to the power of 12 times more luminous, all squeezed into an area which is less than probably several parsecs in size. Those are the upper limits given by the resolution of the observations. This is an image of the first quasar which was discovered. Quasars are nothing but galaxies with abnormally luminous nuclei, as we understand them today, spewing out again jets of plasma at velocities close to that of light. And these jets can travel very large distances, up to 5 million parsecs, 15 million light years or so. These nuclei of active galactic nuclei can vary very rapidly, and they have very prominent emission lines. Okay, and these are all believed to be powered by a supermassive black hole at the center, whose mass can range from about 1 million solar masses to about 1 billion solar masses. So this is the story that I'm going to tell you today, but I've introduced you to a class of galaxies called supermassive black holes. And I wanted to start off with the Event Horizon Telescope because that is where microwave engineering is involved. But black holes occur over a range of masses, right from puny, like the mass of our sun, a few times more than the mass of our sun, to about 100 solar masses. They are called stellar mass black holes. They occur in binary systems. They also spew out jets and are called microquasars because they have similar physics, possibly similar phenomenology, but the luminosity is orders and orders of magnitude lower. Then a field which is growing up in recent times is what are called intermediate black holes. Intermediate mass black holes goes from about 100 solar masses to about 1 million solar masses. And then you have supermassive black holes, which are 1 million solar masses to about 10 billion solar masses or billion solar masses of that order, which I just introduced you to, which reside in the nuclei of active galaxies. We also believe that primordial black holes may have formed in the early stages of the evolution of the universe, which could be much smaller than even stellar mass black holes. But we have no observational evidence of that, and so I will not touch upon that in today's lecture because that is largely a theoretical ideas, but it is plausible, but we don't have much ideas right now. So let me first start and give you a very brief introduction to how the historical ideas developed. I'm keeping an eye on the time so that I don't overshoot too much. How did it evolve? It evolved actually quite a long time ago because it was based on Newton's laws of gravitation. And Newton actually thought of the Cannonball Experiment. Now, you all know about gravitation, so I'm not going to go into great details about that. But he thought of an experiment where he said that if he went above a tallish mountain, it was pretty tall, you can work that out yourself, that if you threw a ball vertically down, it will come down. If you threw it at a certain velocity, so 6,000 meters per second, it's going to come and hit the earth. It's just like when you throw a cricket ball or any ball, gravity is going to pull it down. But if you throw it for his height of the mountain, which he took, at 7,300 meters per second, it's going to circle around and come back to the same place. More than that, it's going to have an elliptical kind of path, and then if it is greater than the escape velocity, it's going to escape. So Newton actually went and generalized that to saying that if it can go around and come back to itself, the moon is also following the same orbit, and he applied his laws of gravitation to the moon and other celestial bodies, and we had a universal law of gravitation. But from this basic treatise, we have a measurement or an estimate of the escape velocity, which is required to escape from the gravitational influence of the Earth. In the meantime, you'll notice that Romer had measured the velocity of light. He was the first one by looking at eclipses of Io, the satellite of Jupiter, at different times of the year. He was able to estimate the velocity of light, which was the first really solid measurement. Earlier, people thought it was immeasurable or unmeasurable. And knowing that there is a velocity of light, John Michell, who was a clergyman, a philosopher, and he sort of speculated that if a star is massive enough, that light would not be able to leave if gravitation is sufficiently large. He said, should such an object really exist in nature, its light could never reach us. Independently, but a little later, Laplace, whose Laplace transforms you have learned, he sort of also described massive stars from which light could not escape. But they relied on these old ideas of Newtonian gravity, and there was a fundamental problems with Newtonian gravity, even though there was a resounding success in trying to explain everyday phenomena, right? And that was, how does it act actually? Why does it act? Why do two objects, pull each other? And Newton himself did not have a clue. He said, the cause of gravity is what I do not pretend to know. This is just a quote from a long letter which he wrote to Richard Bentley, who was again a polymath, a philosopher, and was also master of Trinity College at Cambridge. But Newton gave us a mathematical formulation of the effects of gravity. It was left to Albert Einstein to work out that gravity is not really a force, but matter actually bends space-time. It leads to a curvature, and objects just follow this curvature in shortest possible path, which is called geodesics. Einstein's gravity also showed that if curvature is weak, the solutions are similar to those of Newtonian formulation. So Newton's formulation was subsumed into Einstein's gravity, but it also gave us a deeper understanding of how it operates. So his work was published in 1915, The Field Equations of Gravitation, and it was described by John Wheeler, the famous physicist, as space-time tells matter how to move, matter tells space-time how to curve. So we now have a curved geometry. It's not flat geometry, which we learned in our high schools, which is all due to Euclid about 330 years before the Common Era. So it's more than about 2,500 years ago or so, 2,300, 400 years ago. Today we know that space can have curvature. If it is curved like a sphere, you'll have three angles of a triangle greater than 180 degrees. In Euclidean space is 180 degrees. In hyperbolic surfaces, it could be less than 180 degrees. So this formulation of gravity is sometimes compared to Escher's drawings of Hans, the Dutch sort of thinker and artist. So Einstein's gravity leads to description of the curvature of space-time by a formulation called the metric of space-time. In the Friedmann-Lemaitre-Robertson-Walker matrix describes our universe, which is homogeneous and isotropic on large scales. And as I just mentioned, curvature of space affects the motion of bodies, including light rays. And on a larger scale, the universe is flat. Just have a look at this figure. When there is a body, the space is curved around it. When further away from the influence, the space is nearly flat. And objects, and including light rays, are going to follow these curved space-time, which is indicated by the curved lines over there. And space can expand as well. Space, just as the universe is expanding, and it can carry whole galaxies with it. Now, Einstein actually derived his equations, as I said, after a lot of work in 1915, 10 years after working out a special theory of relativity. And soon after he worked this out, a German artillery lieutenant, Karl Schwarzschild, who was in his trenches fighting the war for Germany. I don't know what led him to fight the war, but nationalism, the bogey of nationalism sometimes does strange things to people. And he received a packet one day, one night, when he was in the trenches. It was a rather bulky packet. He took the risk of opening it, read it with a very dim light, and it was Einstein's work on gravitation. And amazingly, within a week, amidst all the gunfire, as he said, he took time off to wander through Einstein's minds, and he was the first one to arrive at a solution of Einstein's equations. And that solution is a solution of a stationary black hole. A black hole which is a singularity from which matter cannot escape or light cannot escape if it is within a certain radius called the Schwarzschild radius. It's a singularity, it can be a very dense object. If you remember earlier when I talked about Laplace and Michel, I talked about a massive star from which light cannot escape. They did not think about very compact objects because the physics of neutron stars and black holes were not really known at that point of time. And the term black holes got coined by John Wheeler. It didn't get coined by John Wheeler. I believe it was in a lecture where a graduate student suggested it, and John Wheeler picked it up and used it. The Schwarzschild radius is given by scales with only the mass of the object. It's given by 2gm upon c squared, and m over there is given in terms of the solar mass, 2.95 kilometers. I have given you the Schwarzschild radius for objects like the sun, the earth, and the moon, and a supermassive black hole. You can see that for all these objects, they are actually well within the geometrical radius of the object. So they make no difference in terms of the behavior of this object on large scales. Whereas you can see a supermassive black hole, it is effectively a singularity. The event horizon is this inner ball written over here, within which even light cannot escape. This is the photon sphere, where light will be traveled into unstable circular orbits. Beyond that is the accretion disk with the inner one given by the innermost stable circular orbit. And when it gets inside this, it will actually get inside the black hole, never to be retrieved again. And right in the middle is a singularity. And relativistic jets squirt out. We don't know exactly from which point, but we know that these are the monsters from which they come out. Schwarzschild solution Schwarzschild arrived at a solution of Einstein's equations way back within a week, but we had to wait for a very long period of time for the next solution, which was worked out by Roy Kerr for not a stationary black hole, but a rotating black hole. A rotating black hole affects the inner stable orbit. You can extract energy more efficiently out of it, and these have become the engines from which energy can be extracted to power some of the most luminous objects that we see. So let me try with giving you a brief historical introduction. You can ask questions in between if you wish to. Okay, I'm going very rapidly because I'm not going to do any mathematics over here. I'll just give you an overview. Let's first have a peep at the stellar mass black holes. Stellar mass, as I said, is less than about 100 solar masses. But you see that most of them are actually much smaller than 100 solar masses. How did it? Now, it was a theoretical construct. Einstein, Schwarzschild found a solution, and much later, Roy Kerr found a solution. But in the initial days, actually did not attract much attention because we hadn't really come across the kind of monsters which generate the kind of luminosities which we see in quasars and radio galaxies, 10 to the power of 45, 46 Earth per second, coming from a very small volume of space. And also the physics of stellar evolution also, was evolving in those very early days. And then the discoveries of the early stellar mass black holes came along with our understanding of the way stars evolve. These are kind of objects, for example, a low mass star like our sun will evolve into what is called a white dwarf. These are the end products of stellar evolution. This is just to illustrate to you how these stars can be born. They're born in a nebula, they go through an evolutionary phase, and then end up as a white dwarf for the low mass stars. And the high mass stars could end up as a supernovae, which leaves behind a neutron star, which is the kind of objects which Jayakumba, who is here today, works on pulsars, as well as the colleagues from Cotton, Vivek Barwa Thapa, whom we mentioned earlier. And the more massive ones, the most massive ones, end up as stellar mass black holes. So these are where the core collapses and the outer layers explode into giving you a very luminous object called a supernova, leaving behind a remnant which is so compact and so dense that light cannot escape from it. If it is within the event horizon or the Schwarzschild radius, as it is called. What are the kind of masses that we're talking about? These will be slightly model dependent, but just to get some ballpark numbers, if it is less, if a star starts off with less than about 9 solar masses or so, it'll end up as a white dwarf. Between 9 and roughly about 25 solar masses it starts off, it'll be a neutron star. And greater than about 25 solar masses, it'll end up as a black hole. The largest masses of stars that we know of today are in the ballpark of about a couple of hundred solar masses. So how did we discover these stellar mass black holes? It all had to do with opening up another exciting window of the electromagnetic spectrum. The first window that was opened up was a radio window. And the X-ray window, they were trying to look at X-rays reflected by the moon, but they found a very strong X-ray source called SCO X1 towards the constellation Scorpius. They couldn't figure out what it was all about. It took the discovery of another object called Centaurus X3, which was another strong, powerful X-ray source in the constellation Centaurus, which was discovered by the Uhuru satellite, which was launched from Kenya. Uhuru is a Swahili word for freedom. And they found that it was not only, it was a strong X-ray source, it was pulsating, and it had a period as well. And they soon figured out that this was a binary system, with one object being a neutron star, and it had a companion of about 20.5 solar masses, 20 times the mass of the sun. The neutron star would have been born in a supernova explosion, but this binary system survived, and the compact object now accretes matter from the surroundings. You can visualize that when a heavy object, you drop it onto the ground, it'll come to a stop, but the energy which is built up will be dissipated. And here, the amount of energy which is dissipated is radiated as heat in the X-ray region of the spectrum. So the binary systems are the ones which are generating these huge copious amounts of X-rays, whose X-ray luminosity can be in the ballpark of 10 to the power of 36 to 38 Earths per second. Not quite the active galactic nuclei, but you can see they're still 1,000 to 10 to the power of 5 times more luminous than our sun. And that is just in the X-ray region of the spectrum. The different kinds of X-ray binaries, if they are, for example, high mass X-ray binaries, as we saw for Centaurusy, that there's strong stellar winds which falls into the compact objects generating emission, and low mass X-ray binaries, the companion star is of a low mass. So I will not get into too much of details on that, but I just want you to highlight one aspect of it. That when matter is accreting onto an object, there are two things which are happening. One is, of course, it is losing gravitational potential energy as it is falling into a compact object, which will give off, that energy has to be given away, which is radiated away as high temperature radiation in the X-ray region of the spectrum. The plasma gets heated to very high temperatures as gravitational potential energy is converted into other forms. But this energy which is being radiated away will also try to push the matter away, because radiation exerts a pressure. And the balance between the two is what Arthur Eddington worked out and arrived at a maximum luminosity called the Eddington luminosity, which depends only on the mass of the object. And this is about the maximum number that you can get for these X-ray binaries, roughly in that ballpark. They're not all radiating with 100% efficiency, and these are all stellar-sized objects. So now we come across these binary systems where there is a black hole sitting at the center. Some of them, called microquasars, are spewing out jets which you can monitor. These are all non-relativistic plasma which you can monitor at radio frequencies. These are also moving out at nearly the velocity of light, but the total luminosity is much lower than that of the active galactic nuclei that we talked about. Cygnus X1 is one of those where we have a companion star which is about 40 solar masses, and one of the more massive black holes in binary systems, which is about 20 solar masses or so. So you cannot see the black hole directly, but you can infer the existence of the black hole from the X-ray emission which is emitting due to accretion of matter from the surroundings, where the gravitational potential energy is converted into heat as this material swirls around and forms a disk around the black hole. So these are the kinds of galactic size or stellar mass size black holes, and I will also show you how gravitational waves actually gives rise to these black holes. When we come to the intermediate size black holes, then we're talking about 100 to about 10 to the power of 6 solar mass black holes. For a long time, we did not even know whether they existed. They should have existed, because we knew about the existence of the supermassive black holes, and we knew about the existence of the stellar-sized black holes. And the mass we estimate in the stellar blast black holes from the parameters of the binary systems that they are in, and by just applications, in a way, of Kepler's laws of motion. Okay, so it's very basic physics that is applied. There are some technicalities, but the basic physics is Kepler's laws of motion. Now, here is another sort of interesting class of objects which led to the discovery of intermediate mass black holes. Now, I talked about the largest luminosities from stellar mass black holes of about 10 to the power of 38 Earths per second. But soon astronomers began to discover that there were objects which were compact, unresolved, but much more luminous than the Eddington limit, that for stellar-sized black holes. These were called ultraluminous X-ray sources or hyperluminous X-ray sources, and they can accrete matter from its nearby companion. Sometimes a star may pass too close and be gobbled up by these massive black holes over there. And once a material is sort of accreted, it moves around in a disk around it, and it keeps oscillating at various frequencies. And what we found was that some of these oscillation frequencies can be related to the mass of the black hole. So some of these ultraluminous X-ray sources, from the periodicity of oscillations, one was able to get masses of hundreds to thousands of solar masses. Similarly, there are luminous sources which are even far more luminous, 10 to the power of 42 Earths per second, almost appearing to be an AGN, an active galactic nucleus, but these are not sitting at the center of it. This is in the Edge-on Spiral Galaxy and catalogued by the European Southern Observatory. This hyperluminous X-ray source is marked in a red circle. And these are objects which flare up in the flare up in the X-rays, emitting a huge amount of energy. And it is believed that when a nearby star makes a close approach feeding it gas, that these things can blow up. The star can be tidally disturbed or destroyed completely. So one doesn't know how this particular one originated. There are speculations it may have originated from a cannibalized dwarf galaxy, which are galaxies much, much smaller than our own galaxy or galaxies that you're normally familiar with. And people have estimated, the astronomers who discovered this, at least 500, but some go up to about 20,000 solar masses or so. Now, inference of black holes really has to do with looking at the dynamics of gas around it, because you cannot really see the black hole directly. And it is these dynamics which enable us to infer mass, and the basic physics is again similar to Kepler's laws of motion. This is an object in our galaxy, okay, where the molecular gas, again at microwave wavelengths and millimeter wavelengths. So you need telescopes operating, antennas operating at millimeter wavelengths, quite up your street of what you're specializing in. And many of these lines of molecules which exist in our galaxy, in the cold, dense parts of our galaxy and other galaxies, where new stars are forming, are due to molecules whose emission is largely at millimeter or at best centimeter wavelengths, but largely at millimeter wavelengths. What they found was huge amounts of gas emitting hydrogen cyanide from the J, which is the total angular momentum, the quantized angular momentum, 4 to 3 transition. And from the motions of these objects which they have monitored, they infer a mass of about 3 into 10 to the power of solar masses, so about 30,000 solar masses or so. And this has been even taken to much greater heights by looking at motions of gaseous components or motions of stars around them. So this is another particular example in our neighboring galaxy, for example, where right in the center of a globular cluster, they have been able to have the resolution using what are called adaptive optics. This is at the near infrared region of the spectrum, where for the way the velocity changes, this is just a velocity, you can see it is rotating because one side is blue, the other side is red. Blue is coming towards you, red is going away from you. But they also look at the velocity dispersion, because when there's a massive object in the center, the velocity dispersion is going to go up due to the gravitational influence, just as Mercury moves much faster than the Earth, and the Earth moves much faster than Jupiter or Saturn. And these are absolutely exciting areas which one is able to probe from both technological advancements. Technology always plays a vital role in the development of science. It's usually a close relationship between technology and science that drives one another. So governments which talk about supporting applied science just don't understand the history of science or the way science is developed over millennia. Now, intermediate mass black holes as well as stellar mass black holes have also taken a new sort of life with the discovery of gravitational waves and the growth of gravitational waves astronomy. Just to give you a very, very qualitative understanding of gravitational waves is what are gravitational waves? You all know from your microwave engineering as well that accelerated charges produce radiation. And electromagnetic radiation it produces travels through space at the velocity of light. Similarly, Einstein worked out that accelerated masses lead to gravitational radiation. What are gravitational waves? They're perturbations of space due to motion of bodies in a space-time fabric. So Einstein's theory of relativity, general theory of relativity, talks about space-time fabric. And if you perturb the space-time fabric by motions of accelerated bodies, then they're going to lead to perturbations which will move out at the velocity of light. This was predicted by Einstein soon after developing the general theory of relativity. So as the gravitational waves propagate, they stretch and squeeze space. So you and I are all squeezed all the time as gravitational waves pass through us, but the effect is so small that it is completely unnoticeable. So this is what we talked about earlier, that Einstein's general theory of gravity, where space gets curved, and if you perturb this curvature, then this perturbation will propagate outwards as gravitational waves with the velocity of light. So these are just illustrations to show that they have a certain sense of polarization as they travel outwards, and these are seen in the polarized emission as well. What are the frequencies of these gravitational waves? They're extremely small. Electromagnetic waves you've learned from radio waves in the low energy range, about 10 megahertz, which you can detect from Earth, of extraterrestrial, of celestial sources. You obviously have lower frequency electromagnetic waves as well, to the highest frequency gamma rays, about 10 to the power of 20 hertz or so. Gravitational waves are very low frequencies, 10 to the power of minus 9 hertz to about 10,000 hertz. And from the early Big Bang, the suggestions that it could be as low as 10 to the power of minus 16 hertz. And a human year, 20 hertz to about 20 kilohertz or so. So what produces gravitational waves? Any non-spherically symmetric mass can emit gravitational waves. Just to highlight the difference between the huge leap in our understanding that we have made from Newton to Einstein. For example, if the sun disappeared, the Earth would know about it immediately in Newtonian gravity. But we all know from our basic physics that information can propagate at a maximum velocity of light. So that was a fundamental problem with Newtonian gravity. Einstein's theory says if the sun jiggles about, it would move the warp space around it, and this disturbance would move forward at a velocity of light. If it's a perfectly symmetric body, which is just going out and inwards or rotating without any asymmetry, you're not going to get gravitational waves. So, but you'll get gravitational waves when inspiring binaries, supernova explosions because it is never quite symmetric. Rotating objects like pulsars, for example, is never perfectly symmetric. But you will never be able to theoretically get objects, gravitational waves and something which is absolutely spherically symmetric and just going back and forth. If you look at, I will not get into too much of maths, but just to illustrate to you one aspect of it. This is an inspiraling binary system. It warps space-time around it, okay? And the frequency of the gravitational waves, this theory tells us, is about twice the frequency of the orbit. And let me just take an orbit of 1 hour, okay, 1 hour orbit. The frequency of the gravitational waves, if you work out, would be about 3.6 times the distance, the average distance from the Earth to the Sun. So this is when it has an orbit of 1 hour. And if you see that how long, what is this in terms of the diameter of the Earth, it's a tiny little fraction. So it's very difficult to detect these waves. But these waves increase in the energy loss as well as the frequency when it gets closer and closer. A is a semi-major axis. Just don't worry about the rest of the equation. So it varies inversely as a to the power of 5. So there's a very strong dependence. And that is what led to the detection of gravitational waves, where compact objects like neutron stars or a neutron star and black hole, or a black hole and black hole, can get closer and closer together. They will combine together, and then there will be a ring down. And this is the kind of signal which you expect. And this has been detected by the laser interferometers which have been built up. They can detect changes in the interferometer about the size of a proton over a 4-kilometer distance, but we'll not spend time today because our focus is on black holes. But as you can see, as a black hole separation goes lower, okay, separation keeps decreasing, the velocity keeps increasing, and the frequency keeps increasing. And this is what is called the chirp signal. And from all the information, from this information, you can go and detect, you can go and infer the mass of the black hole. You can also infer the spin of the black hole. And now with more gravitational wave detectors coming up, one will be able to even localize it better. This one is 36 and 29 solar mass 2 black holes, which have coalesced to form a final black hole of 62 solar masses. And 3 solar masses of energy is just radiated away as gravitational waves. It's just that the change is very small, it's difficult to detect, but we must be going through gravitational waves all the time. So those were stellar-sized black holes. I'll just give you one example of an intermediate-sized black hole. This was an object which was detected by the gravitational wave detectors in 2019, 21st of May. This is the way it is named right now. I suppose once they detect it more frequently with more detectors, more sensitive, one may have to think of alternative ways as well. But this is in the intermediate mass black hole. So gravity waves has really opened up a completely new window of detecting black holes. This is updated as of 2020. This particular site keeps updating it. Mine may not be the most recent, but it's not too old either. So you can see there's a whole range of stellar-sized black holes which have been detected by the gravitational wave detectors. Smaller masses, these are the electromagnetic ones which have been detected, which have been inferred as we talked about earlier, and these are electromagnetic neutron stars. There's also LIGO Virgo gravitational wave neutron stars, and you can see that you're pushing this further and further into it. Now, how much further can we push? It all depends on how much sensitivity and the frequency at which the gravitational wave is emitted. If you go to more massive objects, the frequency is lower. Today, with terrestrial interferometers, you're sort of looking at stellar size or the lower end of the intermediate mass black holes. If you want to get higher mass supermassive black holes merging together, the frequency is much lower. And the way we can detect them is by accurate timing of pulsars. And this is what Jaikomba has been very actively involved in. And perhaps you could ask him someday to give a talk, because they have been getting very interesting results from the Indian pulsar timing array as well, which is part of global timing of pulsars. But this is an area which gravitational waves can be detected via accurate timing at nanosecond levels of accuracy of a whole array of what are called millisecond pulsars. In the intermediate range, there are plans now of putting up an interferometer in space. It is because of the detection of gravitational waves by LIGO and Virgo, the terrestrial gravitational wave detectors, that these things are being funded, and they look exciting prospects for the years ahead. And these are for the young sort of budding physicists, astronomers, engineers, because it is not just astronomy that works alone. It's cutting-edge technology at all levels that operate in these regimes, that when you're trying to do cutting-edge science, you're also using cutting-edge technology. So I will come to the last part, or nearly the last part of my talk, which I started off with. That is supermassive black holes. So I'm not doing too badly for time. So I'll probably may go a wee bit slower than I've done so far, but you feel free to stop me at any time if you want to ask a question. I mentioned about the two of the active galactic nuclei, or even three, M87, Centaurus A, and 3C273, the first quasar which was discovered. And here I'm just listing the X-ray energies. The normal galaxy like our own, or the Andromeda Nebula, which is given over here, you can see is far, far less luminous. And not only is this highly luminous, but all this is coming from a point-like object in the center of the galaxy. And this is where the X-ray luminosity is originating. What led us to look at these objects in terms of supermassive black holes? How do we get to it? Now, these objects, when they were imaged in great detail, one could see jets in them. I showed you examples of those. Here I'm showing you just three images from the Giant Meter Wave Radio Telescope projects I've been involved with. This is one of the largest giant radio galaxies. Till 2 months ago, this was the largest giant radio galaxy. This has just recently been surpassed by an object discovered with the array centered in Netherlands called a low-frequency array. This is the same kind of electronic engineering, but at low radio frequencies rather than microwaves. This is a GMRT object where this is an object where the jets are probably processing, because the black hole itself is processing like a top, must have been disturbed at some point of time. And images which we have made using both the GMRT and LOFAR. And these are objects where the nucleus, the black hole, may switch off the jet and then restart again. So these are all interesting physics, and the implications of this is something which many of us worry about and try to understand. But when I talk about this large energy, we have to also see what is it that led us to believe that these are likely to be black holes. But before going to that, let me just show you what a normal galaxy like our own, if you took a spectrum of it, what would it look like? The spectrum would be dominated by absorption lines like the one shown over here. The elements are marked over there. And the reason is that stars, if you take a spectrum of our sun or any other star, you will, or almost all other stars, some are exotic stars which have emission lines, that you will find that they're dominated by absorption lines. So when you take a spectrum of the entire galaxy, you will see all the spectra of the stars added up and you'll get an absorption line spectrum. The reason why I'm trying to show you this is the next spectrum. This is a galaxy, but when you take a spectrum of the nucleus, it is hot gas. Hot gas, these are not absorption lines, these are giving you emission lines. And these emission lines are zipping about, many of them, with velocities of thousands of kilometers per second. And that is why these lines get very wide. These are all relevant towards our goal of trying to understand why we need black holes. Now, you remember I told you about the maximum luminosity that an accreting object can take because once it is accreting, the accreting matter will give out radiation. If the radiation gets too big, it will halt the accretion. So that luminosity is called the Eddington luminosity, which just depends on the 10 to the power of 38 m divided by m sun ergs per second. This is the same expression given in SI or MKS units in watts. And we talked about the Schwarzschild radius, which also depends on mass. Now you look at this. When I talk about 10 to the power of 46 ergs per second, I need an object of about 10 to the power of 8 solar masses. And these objects are point-like. And there is no other way that I can have a point-like object of 100 million solar masses except as a black hole. Whatever theoretical difficulties I might have with the singularity, it has to be subsumed in some bigger theory. But there is no other way. There's no star cluster of 100 million solar masses in a point-like object that will not evolve into a black hole. And that is not all. I showed you the broad lines that on the spectrum, which are zipping about with thousands of kilometers velocity. If I can estimate the distance from the nucleus of those objects, I can estimate what is the mass of the central object. That will give you masses of millions to billions of solar masses, depending on the particular galaxy that you're looking at. And these galaxies of the nuclear regions also vary. And you can look at the time scales over which they vary, because any variation that you see will have to have coherence over the length scales that you're talking about. And then you can estimate what the mass of the object is. And all these arguments lead us to that there must be massive, supermassive black holes lurking in the nuclei of this active galactic nucleus. And these are, if you compare different methods, there are differences, but they're also broadly similar. And you can estimate distances of these lines from the center, because the lines vary response to variation close to the black hole, and from the time delay, because the signals will travel at the velocity of light, you can estimate these distances, and that will also gives you an estimate of the mass. So you can see that variability plus the kind of luminosities which you require and the line widths themselves, which are due to random motions, all lead to the fact that you need massive objects lurking in the central regions of galaxies. And this have to be in the mass scale of millions to billions of solar masses. Early evidence that such objects exist, or this scenario that there is a supermassive black hole which is accreting matter. This accreting matter is responsible for the large energies and the luminosities that we see. Came from observations like the Hubble Space Telescope, but we saw this telltale kind of images. That there appears to be this kind of structure, there is a dim in the emission, then there is emission from the center, which is obviously not from the black hole, but something associated with the black hole. This was like a smoking gun evidence. You want to be able to do better, as has been done for M87, the first image which I showed you. But M87 image is just 2 years old, 2019 or 3 years old. 2019, and today we are in 2022. What happened in the interim? In the interim, what people try to do is, for example, this is another galaxy in the Virgo cluster of galaxies. What they try to do is look at the motions of gas. So you'll find that the entire estimate of black holes is trying to look at the effects of its motion, or effects on motion, or effects on the properties that we see, which we will see in a little bit more in a short while. So when they put a slit across it and looked at the motion of the gas, they found that it was moving at about 400 kilometers per second, and the distance was very small from what they could infer with the resolutions they had. Okay, let me just close this phone. Okay, with the resolutions they had, they could put a limit of about 26 light years. So with that limit, they could estimate that it had to be about at least 300 million solar masses. So these are measurements at the optical region of the spectrum. But at radio one can do better. And if an object is nearby, you can also do better. So let's see what we have managed with a relatively nearby galaxy called NGC 4258. It's about 23.5 million light years away. The yellow and red are visible at the infrared. The blue and the purple show X-ray and radio emission, shock-heated gas, as well as jets squirting out from the nucleus of the active galaxy. Now, this particular galaxy, as well as today we know many galaxies, have strong water vapor emission, maser emission, from right in the nuclear region of the galaxy. And water vapor maser emission is again in your domain, outer microwave region of the spectrum. This is at 22.2 gigahertz, correspond to a wavelength of about 1.3 centimeters. You can go and image where these water vapor emission spots are, because you can see the spectrum over here. Okay, spectrum over here spanning a large velocity range or a large frequency range. You can map each of these spots and see where they're coming from. And then if you had the spectral resolution as well as the spatial resolution, you can find out where they're located and how fast they're moving and in which direction they're moving. And when you do that, you find that there is a disk structure around it, just as theoretically we had speculated or postulated. Some of these spots are coming towards us, some of these spots are going away from you. So this is a rotating disk, slightly warped, but you can go and apply Kepler's laws of motion, estimate it, and you can see it is 36 million solar masses in size. You can go very close to it, you can image, you can see R straight away, and you can go and estimate the mass of the black hole. Similarly, for example, I've shown examples of gas motions that can be done. M87, this was done earlier. Today we have a factor of slightly less than a factor of 2 larger from the kind of very detailed imaging which we saw earlier. And this is a very recent piece of work, 4 years old. And it's just absolutely amazing and fantastic observations at a near infrared region of the spectrum with what is called a very large telescopes. These are which have been linked up as interferometers by an instrument called Gravity, and they have gone to milliarc second resolutions, which would have been impossible at optical wavelengths. The Hubble Space Telescope has a resolution of about 50 milliarc seconds, but they have been able to combine these signals, just the radio interferometers have done, to synthesize a telescope on the ground, an infrared telescope of 130 meters in size. And they have tried to map the stars or gas regions over here and estimate its velocity. Okay, estimates its velocity. You can see that there's a systematic difference, red on one side, blue on the other, and they can, from the motion and the dispersion in velocity, they have estimated about 3 into 10 to the power of 8 solar masses. I'll take probably another 5 or 10 minutes. 5 minutes. Okay, I'm on schedule to finish in an hour, after which we'll take questions. So the other sort of very interesting way of trying to estimate lines, estimate black hole masses, is from a different region of the electromagnetic spectrum. As you know, elements emit lines which are characteristic of the particular elements. Now, iron is very tightly bound, and the iron in the inner K shell, when there is a transition from the next higher shell to the lower one, it emits a line at 6.4 kilo electron volts. In the accretion disk around a black hole, the gas would be at very high temperatures where you'd be able to see this line. Because to take it to the high level, you need the high energy in the inner regions of the accretion disk. And if the disk is rotating, as we have seen in other cases, and if it was just rotating, Newtonian physics would have told you redshift and blueshift. Special relativity will tell you that the one coming towards you will be enhanced, and so the intensity will go up. General theory relativity will tell you that they will lose energy trying to come out of the gravitational potential well, and this is what you're going to see. And the line profile combined together is what you'll see. So this has been done for a number of objects. This is a particular kind of galaxy called the Seaford galaxy. This line profile is so similar to what we have seen over there, but there are various phases of this particular galaxy as well. I will not get into details, but this calculation has been done for both Schwarzschild black holes as well as rotating black holes, and using those simulations, one can also infer how rapidly the black hole may be spinning. So we can not only know the mass of our black hole, but also the spin of our black hole. Our galaxy is very special to us, obviously, and is also very close by, so we can try and estimate what is the mass of the supermassive black hole sitting in the center of our own galaxy. Just to remind you, our galaxy is a spiral galaxy, and it has a bulge. We are about 28,000 light years from the center, and you could count 3, 6, 9, 11, 10 to the power of 11 stars is what our galaxy contains. These are old stars. The disk is where new stars are forming. We also have a halo of old stars, and we are all embedded in a huge dark matter halo. This is what our galaxy would look like if you could get out of the galaxy and peer down as a face-on rather than seeing it edge-on. And right in the nuclear region over here is sitting a supermassive black hole. That was suspected from radio observations of a compact radio source. There have also been activity going on in the central region of our galaxy. This is a huge bubble of energy in the gamma rays, which is coming out. 25,000 light years, very similar to the distance of us from the center of our galaxy, but fortunately, it is going in the upward direction, perpendicular to the plane of the galaxy, along the galaxy minor axis. So there is clearly activity, although it is not quite a jet kind of structure. How do we estimate the mass of this galaxy? Many of you may be familiar with it because this got a Nobel Prize a few years ago. And I will just show you, play this animation over here, where from infrared observations, they have monitored, two groups have monitored the motion of stars in the neighborhood. You can see that when the particular star which comes closest to the black hole marked in the center, called S02, and as it gets closer to the black hole, it moves faster, and then it will be slowing down. This is just Kepler's laws of motion. Application of Kepler's laws of motion by monitoring these stars have actually led to estimation of the mass of our black hole of close to about 4 million times the mass of our sun. You can see the time lapse over here. They have actually monitored these objects using very high angular resolution. And this has been possible because of very advanced techniques of trying to get high resolution using adaptive optics and aptive optics so that the effects of the atmosphere is blurred over there. This particular simulation goes till about 2020, and this has been a fantastic piece of work which earned Andrea Ghez and Reinhard Genzel, the two of the leaders of this project, to getting the Nobel Prize in 2020, a couple of years ago. This is just a three-dimensional animation of it, produced by Andrea Gez's group, and it's just beautiful to just watch it, watch the stars move in 3 dimensions, and they have monitored the motions, month after month, year after year after year, for decades together. You can see how perseverance has paid off, and not only fetched a Nobel Prize, but have provided a very accurate mass of the black hole, which is in the center of our own galaxy. The thing is, you can ask yourself that could it be something else? Could it be a globular cluster? Could it be anything else? But when you look at this object and look at this orbit of S02, getting so close to this object, because of the high angular resolution which you have been able to get, that you can rule out almost every other object and say that this has got to be a black hole. A singularity is not the best. In each theory which is singularity, one is not very happy about, but the fact that black holes exist, I think, is universally accepted. Perhaps, hopefully, someday we will also understand these singularities. When you measure the mass of the black holes, one also finds that these are very closely related to the mass of the bulge of galaxies, like the bulge in our own galaxy. The higher the bulge, the more massive the bulge is, which you can estimate from the velocity dispersion, the more massive the black hole sitting inside it. So the black holes seem to be growing along with the galaxy itself. This was a relation which was reported by Megorian et al., and it's referred to as the Megorian relationship. So understanding how black holes grow, how they evolve, I've just listed below some of the leading questions. We need more complete demographics. We still have, probably less than 50 stellar mass black holes. We have far fewer intermediate-sized black holes. Massive black holes have invert for a much larger number. How do they form? Are the intermediate mass black holes seeds for larger black holes? What happened to the primordial black holes if they form at all? How do they evolve? What are the close relationships between galaxy evolution and black hole evolution? How do these jets squirting out of black holes affect the interstellar medium of the host galaxies? How do they affect the intergalactic medium? How does it affect the evolution of our galaxy itself? How do gas and magnetic fields behave in regions of such intense gravity? How are these jets launched? What are the physical properties of black holes that determine the nature of this plasma and how these jets are formed? So a lot of work is still required, both in theoretical work and simulations, as well as a lot more observational work. So this gives you a brief overview of our understanding of black holes, tracing it from a historical outline of when a clergyman and a mathematicians in England and France thought about light not escaping from massive stars to where we are today. Fantastic progress has been made, not only in the theoretical domain, big breakthrough, of course, being Einstein's general theory of relativity and understanding of gravity, but all the technological advances which have made it possible to try and probe these elusive objects, whether it be in binary systems, binary stellar systems, whether it be in globular clusters, whether it may be just lurking around, traveling around in our galaxy, so that huge masses of gas whose dynamics have been affected by these intermediate mass black holes, as we saw. Are they going to coalesce with the central black hole in our own galaxy someday? Or are there just hundreds of them and they're there and we haven't found them? And are they going to form these massive supermassive black holes? We're still actually quite clueless, although there are a lot of interesting ideas and theoretical work which have developed along with the fantastic advances in observational work aided by technology. So I will end over here. I think I have spent taken within an hour and 20 minutes. Yeah. Okay. So I can take any questions that you would like. If you wanted to stop sharing, I can stop sharing as well.
Yes. Thank you very much. Yes, Professor Rajab, please continue.
Just thank him. And because we are not in this field, what we understand is how to analyze the microwave signals, not much beyond that. So any questions from your side, Pallav, or anybody else? that Professor Saikia can illuminate us on. Anything follow?
Can similar localization of spin or mass happen in atomic nucleus?
Sorry, Pushkar, just repeat your question.
Like, can similar localization of spin or mass happen in atomic nucleus? Is there in atomic nucleus?
In atomic physics, we can do that, no? I mean, the quantum properties of an atomic nucleus have been studied and have been determined, but that is in the quantum domain. Whereas what I'm talking about is much larger scale. And the thing is that the quantum mechanical spin of the nuclear components, they will follow the laws of quantum mechanics. Spin would be quantized in the case of an electron spin or a proton spin or a neutron spin. They're quantized numbers. Whereas as far as the spin of a black hole is concerned, then we still have not been able to have a theory of gravity which is quantized. So that is another frontier area where, for example, to understand the singularity, we probably get into the quantum domain, which we have not been able to quantize gravity. So that is another exciting area of research. But your question about nuclear particles spin and the black hole mass spin are slightly different because the laws of quantum mechanics apply to the small scale particles, and they are quantized quantities coming from quantum mechanics. Whereas here we are talking about the overall angular momentum of the black hole. Okay, and that is not a quantized quantity. This is in a large scale. We're talking of objects which are millions of solar masses in mass, or billions of solar masses from stellar-sized objects, stellar mass objects. Any other questions?
Yeah, I want to ask you one question.
Please.
But first of all, I must say that your talk, Professor Saikia, it was a very insightful and informative talk. So being a microwave engineer, we are very much fortunate to hear this talk from you. So I have one. Thank you, sir. And sir, I have one question. That question is that can we extract energy from black hole for utilization?
Actually, the thing is that we are there are two things actually. Okay, that when we see these jets coming out. Okay, one is that we are extracting energy from the black hole. We are extracting energy from the black hole, and there are clever techniques which have been worked out by which you can take you can extract the rotational energy of the black hole to power some of the jets which I showed you. Okay, and also what happens is that the accretion disk and the black hole could be threaded by magnetic fields. So when the black hole keeps spinning, you'll also build up magnetic stresses, which can also work towards actually extracting energy out of the black hole. That is on the large scale. Okay, on the large scale where I talk about the jets squirting out of the nucleus, whether it be microquasars from stellar-sized objects or active galactic nuclei from the kind of galaxies that I showed you, so we can extract energy from the rotational energy of the black hole. Obviously, when there is matter within the event horizon, which is from where light also cannot escape, we cannot extract energy from that. But we can extract energy from an area outside that, called the ergosphere. So we can extract energy from the accretion disk. We can extract energy from the ergosphere. But on the other hand, once you're within the event horizon, you cannot do that. Okay. The other aspect is the work of Stephen Hawking. For example, in physics, you can think of a perfect vacuum as consisting of particles and antiparticles, which given the Heisenberg's uncertainty principle, can keep creating and then recombining all the time. It keeps happening. But what Stephen Hawking argued was that suppose a particle-antiparticle pair gets created very near to the event horizon of the black hole, and one of them accidentally falls into the black hole. Then the other one will actually, escape out. So there is radiation which is coming out from the black hole. So he tried to calculate a temperature and a time scale for that to happen, to have any observable consequences. But the temperature is extremely low, and the time scales are much, much larger than the age of the universe for the kind of black holes that we're talking about. So it has no observational consequences, but on the other hand, it is again a viable theoretical process. But in terms of understanding the energetics of the jets that we talked about, we do extract energy from the black hole, the rotational energy of the black hole, as well as from the magnetic field which gets spun up when the black holes rotate. All right?
Thank you, sir. Thank you, sir.
Yeah.
But with consequence to your answer, I just want to ask one more question with your answer. That you were saying that when one particle is falling on the black hole and other one is escaping out, then there will be the radiation from the black hole, right? That you were saying.
That is what is called Hawking radiation.
Okay, so what is the reason behind that?
Reason behind that is that, for example, if I create a particle-antiparticle pair, okay, particle and normally what would happen in a vacuum is that they will recombine and the status quo will remain. But suppose one particle gets inside, then the other particle will move out, and an accelerated particle is going to give out radiation.
Okay. Thank you, sir.
Sir, I have a question,
Please,
if I may.
Please, Shreya.
So this black hole image was formed with the help of Event Horizon Telescope. It works on the principle of radio astronomy, means it sends microwave. Correct, sir?
Absolutely, yeah.
Okay, so if we use this LIGO technology, LIGO observatories, we will be able to map the gravity, it detects gravitational waves. So we can map where the gravitation is the strongest in our universe. So will that help in future to create the geometry of universe, or is that far-fetched? Or
actually, the thing is that today, from a variety of observations, we think we have a reasonably good idea of the large-scale structure, the geometry, and evolution of the universe. I mean, there is a lot of observations which are consistent with theoretical understanding as well as observational data. In fact, what I should have shown you, because I was talking about black holes, is that there is a relic radiation from the early hot Big Bang origin of the universe, which is a perfect blackbody radiation, because the universe initially was extremely hot and opaque, and once it expanded, then it began to cool. And at a certain point, the radiation and matter decoupled, and that radiation continued to cool with the expansion of the universe. Our universe is expanding, and that radiation today is at a temperature of about 2.73 degrees Kelvin, which is in the microwave region. It peaks at about 160 gigahertz. Now, the thing is that, so as far as the large-scale structure of the universe is concerned, there is a whole spectrum of observations, from abundances of elements, cosmic microwave background, the way galaxies are structured, the way galaxies form clusters, the way dark matter is distributed, which gives us a reasonable idea. Now, the thing is that what is the Event Horizon Telescope going to give us? What is LIGO going to give us? See, Event Horizon Telescope, for example, as I mentioned, the wavelength of the resolution is given by the wavelength divided by the diameter. So as far as the Event Horizon Telescope is concerned, the diameter on the Earth base, it has gone from peak to peak. I mean, more telescopes will enable you to make more detailed and more sensitive images. But unless you have another antennas in space, you'll not be able to improve the resolution. But the Event Horizon Telescope has enabled us to image the first black hole. It has helped us to image the regions where jets are being launched in active galaxies, and try to understand the relationship between jet launching and black holes. Okay, so that is one kind of information which microwave engineering or microwave telescopes have given us, and that will continue to be pursued because right now, even today, M87, I've showed you the microwave image or the millimeter wave image, but they're trying to combine this with data at all other wavelengths to construct a complete picture of what is going on, monitoring it regularly to see what kind of variations might take place, where the high energy photons generated, etc. So there's a whole lot of physics on that front. As far as LIGO is concerned, LIGO's objective is to detect gravitational waves. Okay. Now, gravitational waves can occur due to the mergers of, one way is mergers of spirals, as we saw earlier. Mergers of black holes is what I tried to highlight, but mergers of neutron stars as well. And there has been mergers of neutron stars which have been observed across the electromagnetic spectrum. So we have understood through that how some of the heavier elements may have formed. From the spectra which you take when neutron stars merge. But we have been able to estimate the masses of these neutron stars by detecting the gravitational waves from them. So there's a whole lot of physics of these objects, where they lie, how frequently they occur. And every time a new one is detected, we find that there are new advances or new progress in our understandings. And today, because we are not sensitive to supermassive black holes or much more massive black holes from terrestrial interferometers, there is talk, as I said, of putting a space interferometer, like LIGO, but in space, called LISA. And then there is, as I mentioned, about Jayakumba's and others' work on trying to detect gravitational waves by timing millisecond pulsars, because when these gravitational waves propagate, they will disturb these pulsars in a minute way, which will affect their periods. So if you had a whole lot of them, you'd be able to find them. So there are different kinds of information which you're getting from gravitational waves and different kinds of information which you're getting from the Event Horizon Telescope. Now, there's a LIGO which is being built in India right now in collaboration with LIGO, US, and that will actually help us localize the origin of the black holes better. I mean, today once you localize it, then there's much more new physics to be learned. Is it coming? Which galaxy is it coming from? What else is it going to tell us about? Okay, so today's astronomy is a multi-messenger astronomy. So we try to get all kinds of information, not only across the electromagnetic spectrum, but from high energy particles, cosmic ray particles. For example, the M87 jet is generating cosmic ray particles. The highest energy cosmic rays are probably being generated in events like jets in active galactic nuclei. Now they're going to give us pictures of the physics of how these particles are accelerated in the vicinity of black holes. So you can see over here that as microwave engineers, once you think about engineering to build telescopes to image objects at that level of resolution, you're leading the way to actually a whole lot of other questions. So these are all complementary information which goes to develop a deeper understanding. Is that clear, Shreya?
Yes, sir. Thank you.
Okay. Any other questions?
Professor Ruba, can you please explain what's the difference between no-hair theorem and the black hole information paradox?
No?
The no-hair theorem of black holes and the information paradox, what's the difference between them?
Oh, okay. No-hair theorem basically says that a black hole is a very simple object, all right? It is defined by basically three quantities: mass, angular momentum, and charge. All right, mass, angular momentum, and charge. Okay, so that is so conceptually, it's a very, very, very simple description of a black hole, and that description is sort of referred to as the no-hair theorem. Now, as far as the information paradox is concerned, now, for example, if I look at it, okay, that once an object goes inside a black hole, I mean, today I talked about the black hole being characterized by the no-hair theorem of just charge, mass, and angular momentum. Now, if I look at, for example, suppose I had, the entire library at Alexandria, just full of information, getting inside a black hole. So all that wisdom is actually lost, right? because the black hole has just charge, mass, and angular momentum. So what has happened to all that information? Where is all that information gone? Are we going to retrieve it? For example, when seen from outside, because the emission gets redshifted and redshifted and redshifted and redshifted as you approach the black hole to an outside observer. But the observer itself, it will cross the event horizon and get inside. I mean, are some of this information imprinted in the event horizon? We don't really know, actually. But the loss of information because the black hole can be just characterized by three quantities is what is referred to as the information paradox. But the more fundamental question is that the black hole in the solution of Einstein's equation is still a singularity, and that singularity is something which one is not very happy about, because what is a singularity? It's an infinite density point, right? And hopefully that there will be someday a theory which will subsume the singularity and will understand better and will resolve these paradoxes like the information paradox. Okay. All right, Lanyangla.
Thank you, Professor Dhruva, for your time. I guess it's almost 7:45, 7:36. You have been really very kind enough to answer each and every queries and also giving us this time besides your busy schedule, actually, and specifically for like microwave community. We are very closely related specifically. And IEEE has recently also one milestone actually in GMRT telescope.
Yes.
So, and many of our IEEE fellows, they are with very close relationship with radio astronomy. So it's really nice to have a very close connection actually, being same community. And you already said like it's an interdisciplinary subject. Like it's like more of technology and physics and geography, like all coming together once. So thank you, Professor Dhruva, once again for this wonderful time. And I would also like to thank all the audience, because besides having this busy schedule, I have seen like there has been a constant audience like who have been being patient enough to listen to your talk, and it was indeed quite interesting. Thank you once again, Professor Dhruva. I would also like to thank Professor Roger Roy for his time. Professor Roger, you want to comment anything?
No, I just said that, see, I don't have too much of an expertise on this. I have some interest in this, that much I can say. But any work, if we can get from Professor Dhruva Saikia, we can take it up. All of you are here. So myself and yourself, if he gives us some work on this antennas and how to make it, we can think of it. That much only. Okay, thank you very much.
Thank you very much. And Professor Dhruva, we'd really like to invite you physically once everything is fine to our.
Yes, that is one more point. Unless we have an interaction here, we can't proceed very far.
Thanks very much. Thank you very much. It was also nice to see several Cottonians, Okay.
Thank you very much.
Thank you very much. Yeah. Okay. All the best. I'll sign off now. Yeah?
Yes, Professor. Okay. Thank you. Bye.
Hi, Jaikomba. Good to see you. Okay. All the best. Yeah. Bye.
Bye.